And now it's time for some word problems. So, paleontologists can estimate the size of a dinosaur from incomplete skeletal remains. For a carnivorous dinosaur, the relationship between the length s in meters of the skull and the body mass m in kilograms can be expressed using the logarithmic equation. Determine the body mass to the nearest kilogram of an Albertosaurus with a skull length of 0.78. Don't let this equation intimidate you. There's not too much here. There's really only two variables, so we're either looking for the skull length or the mass. In this case, we are looking for the mass. You do want to make sure you're given the right units though. So our skull length is in meters, and yep, in the question it says meters too. Perfect. So I'm going to rewrite 3.6022 log, and in this case we have 0.78, and that's equal to log m minus 3.4444. Now, because this is a natural logarithm, I can actually put the left side into my calculator right away. You don't want to lose any value though, so we get negative 0.3886 dot dot dot. In your calculator, just leave that in there. So we get log m minus 3.49, or sorry, that's 444. 444, and then we're going to add that to both sides, so you get 3.0557 equals to log m. And now we can turn this into an exponential equation. So we got a base 10, so 10 to the power of 3.0557 equals m, or in this case it equals to 1136.85. Now it's just to the nearest kilogram, so it's going to be 1,137 kilograms is our mass. So our next example should have you thinking of our exponential word problems all over again, except for now we can actually solve them without using a graphing calculator. So when an animal dies, the amount of radioactive carbon-14 in its bones decreases. Archaeologists use this fact to determine the age of a fossil based on the amount of C14 remaining. The half-life of C14 is 5,730 years. Head smashed in buffalo jump in southwestern Alberta is recognized as the best example of a buffalo jump in North America. The oldest bones unearthed at the site had 49.5% of the C14 left. So how old were the bones when they were found? Well, I said already, you probably have to go back to your exponential equation. So that's your y equals ab times x, where y is our amount we have at the end, a is our initial amount, b is going to be like our half-life or whatever's happening, and x is going to be part of how many years it takes for that to occur and how many years we actually have. So in our case, we have 49.5% remaining, or which as a decimal that's 0.495. Now it says that, well, when the dinosaur dies, it should have all of its, or animal dies, it should have all of its starting amount. So it should have 1 to start. Now we're talking half-life, so every so many years we should lose half of its value. So that's why that b, or our base, is going to be 1/2. And we know that it happens every 5,070 years that we lose half. The question is, how many years was it when we actually found it? So I'm going to do that division here, where x is the amount of years it's been dead, and we're going to divide that by 5,730 to see how many times it's actually lost half its value. Now this one part can go away right away, and I'm going to just take the log of both sides. So I'm going to take log 0.495 equals, I'll put this as log 1/2 to the power of x over 5,730. Now I can use my power law, so I can make that into my coefficient. So it becomes x over 5,730 times log 1/2. Now because this is multiplication, I can divide both sides by log 1/2, or 0.5. So log 1/2, and the opposite of dividing is multiplying, so I'm going to multiply both sides by 5,730. So we get that times our logarithm. So log 0.495 all over log 1/2. You can put that in the calculator all at once to find out what x is. And we find that it's 5,813. You can do a little bit of a reasonability check. 49.5% is awfully close to it happening only once. And you can see it happened at 5,730. So yeah, it's dead a little bit longer than that, which makes sense with our question we got, our answer we got.